For this beam, we've been asked to find the internal forces at A and B. Now, the first thing we need to do here is we have to find the reaction forces. So I'm just going to do that first, and then I'll be straight back. Okay, so got those. Could have just seen it by looking at it. Symmetrical, there's no x component, but good to run through it anyway, just to see how the calcs work out. So it's in the middle, so therefore it's shared equally to both sides, that force. So you've got 200 Newton reaction upwards on both sides. FCX must be 0 because the imposed load has no x component. So that was pretty easy. So now we're looking at trying to find the internal forces at A. So let's do that next. So to do that, I've just done a little sketch already, so let me drag this up here. And there's a few different ways of thinking about these internal forces, so if you don't get my explanation, because it's kind of the way I think about it, look online, see if you can find any other explanations, or have a look at Terry Bennett's explanation in his notes, or his videos and in his notes for his course, the statics course. But let me do my best to explain it. So we've already found the reactions for this beam, so we've found all the external forces. All I've done is I've redrawn it and I've split this thing at A, the same as I did when we were looking at the foam elements. And then in my mind, I'm thinking about all the different types of internal forces. And so if you start, let's start with something like this. So you've got a little block like this. You could stretch that, so that internal force would be tension or compression. And what you would talk about is that's a axial force. And the external force for that, usually you show that with an N. So it stands for normal force or axial force. So normal just means it's perpendicular to this face here. So it's a normal force. So that's the first thing we can get. We could get a normal force. The other type of internal force was bending. And what I'm saying here is that one is positive. Okay, so that's the positive version. The negative version would be compression. So you'd squash this block down a little bit. This is the original block up here. So it would get squashed down a bit and it would be going this way. You could still call that N if you wanted to. But when we're thinking about this, the first thing we're going to draw on this section are going to be all the positive forces. So we'll just draw on the positive ones and then we work through our answer. And if the answer turns out to be negative, then the magnitude is negative, then we know we put this in the wrong direction. We need to change it. Okay, so the first type of internal force is an axial force, which could be compression or bending, or internal effect is an axial force. The other one was bending, a bending moment. And remember that was cause, and positive was sagging. So that was the positive, and that's caused by a pure moment at each end. So you might have a moment here and a moment here, and that would be a bending effect. Or we might have shear, so you might start with a shape like so, and it ends up like so. And you've got to force this positive right, positive left, negative right, and so that would be, and usually you'd call that, use a letter V to stand for that. So we're trying to find these internal forces, the forces that do this to an object would cause these deformations. The way we see internal forces is to cut it, and that makes these internal forces external. So we're going to find a bunch of external forces on here, and then we're going to think about, look, what effect is this having? And we're going to find a sign for that internal force. So what's going on inside this beam? And that's going to be our final answer. So, and the way you do that is think about static equilibrium on each side. The first thing we do, so first of all, we redraw the free body diagram, split up into left and right. Eventually, you'll be able to just imagine splitting it up, but I really recommend to start with, you actually do split it up. And what we're going to do is we're going to have our X and Y axes, and we're always going to do, I better do it thin so it doesn't look like another beam so we'll just do like that. We're always going to do Y perpendicular to the beam. So that's going to be the y direction, and we're going to do x in line with the beam or the member, the structural member. So this is going to be x. So if you had a beam like so, and it was at an angle, I don't know, maybe it's supported here and it's got another support here that's a rolling support, then we would be doing y perpendicular and x parallel to that beam. Okay? So we've found our reactions, just going back over where we're at, we've found all the reactions, we've redrawn the free body diagram split up into two parts, and now what we're going to do is we're going to draw the forces that we'd have to apply at this section to find static equilibrium, and we're going to use the usual conventions, and we're going to draw them on so that it would be positive. So I'm looking at this diagram here, this section here. If I want positive axial force, then the external force that causes that is going in this direction on the right hand side. So that what causes tension is a force that way, and usually we'll use an N for that. We'll call it NA because it's at A. Then I'm thinking about shear. So to get a positive shear, we've got up, left, down, right. For this one here, we're on the right hand side, so we're going to do a shear like so. That would give us a positive shear, and we're going to call that one VA. Okay, so for positive shear, the external force, it's not really an external force, only an external force because we split it, but the external force would have to be going down the way to make that positive shear if it's on the right hand side. So that's the way I'm going to draw it. And then we're going to work through the calcs. If the answer came out negative, you'd realize that actually the shear is in the other direction, the force is in the other direction. And it would be a negative shear, as it would be shown here. So a negative shear would be like that. And you'd be going down, left, and up, right. That would be a negative shear. Put that out again. Okay, and the one other thing we need to think about is we could have an internal force that's bending moment, a bending moment. To get a bending moment within the object, you need to apply a pure moment at each end. So we'll give you pure bending moment. So we need to think about that as well. And for the direction of this, again, we're going to do positive. Negative would be like this, hogging, it's called. So it would be this way. And you would have to have a moment down like this on this side and that side. So it would be, what is it, anti-clockwise, clockwise. Positive bending moment is an internal force that causes an object to bend like that. You're going to have negative on this side, positive on this side, the external force. And so we're going to draw this on, assuming that we're going to get positive. So we're going to draw on the moment like that. Okay, and again, we've split it. So the forces that we're drawing on here are kind of like imaginary external forces, and we're going to figure that, we're going to use them to figure out what the internal forces are in this beam. How do we do that? We just treat each side, we'll get to this one in a minute, but what we do for this is we just treat each side, so we're going to take this side first, as if it was an object sitting on its own. And we're going to figure out what shear forces, normal forces, and moments would we need, where did my y go? What forces would we need to get static equilibrium for this? Did I rub out my y at some point? Looks like. So we're saying we're going to take y this way, perpendicular to the beam. So that's the y direction. So it's just the same, the usual rules for rigid body equilibrium. So we're going to use the sum of the x components must be equal to 0, the sum of the y components must be equal to 0, and the sum of the moments must also be equal to 0 to get static equilibrium, to make sure that that half doesn't move. Let's start with sum of fx equals 0. So the sum of the x components equals 0. So now I'm shifting back into the frame of reference x and y. Okay, this is for internal forces. We've made these forces external by cutting it. And now we're thinking about these. The sign of these is in terms of the x and y components, not in terms of this stuff. So it's in terms of the x and y components, just as you would have done before. So the sum of the x components is 0. That 200 is going up the way, so it's going to be positive. So this here means, so it's 200. What other forces have we got? Oh, sorry, x direction. X direction first. So the only x component we've got, this has no x component, neither does anything else except for this normal force, NA. That normal force is there. Compared to the x and y axes, that's going in the positive direction for this one. Excuse me. So we write down NA, we don't have anything to add to it, is equal to 0, done. So we know that there's no axial force on this beam. That makes sense because there's only a force down the way. There's nothing pulling it or pushing it. So the axial force is equal to 0. Let's take the next one. The sum of the y components must also be equal to 0. So what does that mean? Okay, so again, when we're working through this part, it's just like your normal equilibrium. We're not thinking about these definitions for positive and negative. We're using our x and y axes. So what have we got there? So we've got positive 200. It's going positive in the y direction. Then we've got minus VA is equal to, we don't have any others, do we? Nope. Is equal to 0. Therefore, VA is equal to 200. And it's come out positive. So shear or shear force is positive 200 newtons. Okay, and so this is actually negative compared to these axes, but when you're thinking about shear force, okay, that's our internal force, we are thinking about this definition of what's positive and negative. Have I lost my, yeah, no, that's right, up, right, down, left. So up, right, down, left, and so we've got up, right, down, left. So the shear force at that point is the internal force, shear force, is 200 newtons, positive 200 newtons. Even though the imaginary external force is negative, the shear force is positive because of this definition, up, right, down, left, positive. Okay. Next one, and it'll become, as you do a few examples, it'll become a bit clearer. It can get a bit muddy at this stage because it's hard to separate these internal forces from these imaginary external forces because we've got it, blah, 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 blah. But as you go on, it'll become clearer why this is positive. I'll try and be careful to explain that as we go along. So, sum of the moments must also be equal to 0. Have to be a wee bit more careful about this. So we're thinking of the moments about A. So let's just call it the moments about A. Now let's just call it the sum of the moments is 0. Sum of the moments is equal to 0, and I'll call this should really be called MA. So what have we got then? So we're going to do it about this point A. So everything we're going to do is going to be about that point A. Remember, a moment's a free vector, so you could move it anywhere. You wouldn't change the answer. But anyway, we're going to find the moments about A. Why is that good? Because it means that this VA doesn't have a moment and this NA doesn't have a moment. Neither of those are going to have a moment because they go straight through that point. So that moment will turn into 0. So what we're going to be left with is this has got a lever arm to there. It's got a lever arm of 1 meter. Therefore, we're going to have 200 times 1 meter plus, all of these have 0 moment about that point A. Let me just write what we're doing here, about point A. All of those are 0 because they go through the point A, except for this moment. The moment, you have to always add on that moment. And so plus MA, that's correct, plus MA. Be careful, Kevin. Okay, so I'm thinking this must be positive, so I've made a mistake somewhere. So 200 to here. Which direction is it going to rotate it in? It's going to rotate it this way, which is clockwise. Therefore, that should have been negative. Should have been negative, minus 200. Okay, so this one's going this way. That is a negative moment. So therefore we have to write it down as negative. When we get to this point, it's all just the same as we've done before to find static equilibrium, and we'll worry about the definition of positive or negative for internal forces at the end. But MA is anti-clockwise, so it's positive, and we don't have any other moments because it'll go through 0, so equals 0. Therefore, MA is equal to 200. Okay, in this direction, it's 200 in that direction. So it's positive, so we've got the direction right in the diagram. And then we can figure out the moment at A. Moment at A is equal to. So the moment at A, we have got positive to the right. We don't actually have one to the left, but this one is making a moment the other way. That force is making a moment that way. And so therefore, it's this one. So it's positive. Sagging moment, positive on the right-hand side, negative on the left-hand side. That's a positive bending moment. And I'm just going to say bending moment at A. So the internal force is called a bending moment. The internal force is just called a moment. Oops, no units. Newtons, wasn't it? Not kilonewtons. Yep, Newton meters. So the bending moment at A is 200 Newton meters. And it's positive because, well, we would have got a negative here at the end if it was wrong, but that's the positive direction for bending moment. So the bending moment A is positive. Everything done? Yes. So we've got those two answers. And so we could write at A, shear is 200 newtons. You could even put positive 200 newtons. Moment is positive 200 Newton meters. Okay, so that's A. What I'll show you now is just what happens if you do it with the other side. So internal forces at B. So what I might do is just grab this. I'll not grab the whole thing, I'll just grab this one. Oh, it's not at B at all, it's at A again. It's going to be a long example. So it's A from the other side. Now, if this is correct and you work through this procedure, you should get the same answer, including the sign. It should be the same answer. And that's the reason it gets a bit contrived, as you're saying, look, I'm trying to find internal forces. I don't want to get different answers if I think about this side and this side. I just want to be able to say at that point, the shear is this. So what we do here is the same thing again, but we're just thinking about what direction to draw things to get positive, the right positive and negative values. So let me have a look here. So again, let's start with our normal force. A normal force that's positive is going to cause a positive internal force. So tension, in other words. On the left-hand side, it has to be going this way. We're keeping X and Y the same though. So X has come with us. Y is this way. Do you see, did I? No, I didn't. I copied it. That's cool. So Y going this way. Okay, so for all this is a negative, it's the negative direction compared to X. That gives us a positive axial force internally, because positive axial force internally, the external force is going to the left on the left side, and it's going to the right on the right side. So this needs to be going this way to get a positive axial force for the internal force. Then we're thinking about shear. Shear is positive if you got up on the right, and so this time, so that again we'll call that NA. We'll call this VA. And up is positive to the right. Why? because up on the right causes a positive shear. Up, right, down, left, that's how you remember it. So on this side I drew it down the way because I was on this side of this object. For this one here, I'm on this side of the object, so I'm drawing the shear up the way. And for moment, positive is it the moments that make sagging, and so M I'll draw on this way. So far so good. And why is that? Because this is positive bending moment. So the pure moment, that's kind of the external force that we've made by cutting this in half, should be going clockwise. And now we switch our, so once I've drawn those, I switch my thinking back to what we've done previously, where we're looking at positive and negative for what are pure external forces, just external forces. And so I'm switching my thinking back to that while I'm doing this static equilibrium part. So therefore, we're doing the same thing again. The sum, oops, a daisy. The sum of the x components must be equal to 0. Again, it's trivial. NA equals 0. So the axial force is, or there's no axial force. Axial force is 0, first internal force dealt with. So there's no axial force in this. It's not tension or compression, just bending and shear. Next, the sum of the y components must also be 0. What have we got this time? So that means, I suppose that means that as well. So what does that mean? So what y components have we got? Well, we've got this shear force here. We've got applied load here, and we've got a reaction here. We're going to do everything about this point A. So let's just figure that out. So we are going to get, first of all, the moment. That's always applied. It doesn't matter where this is on the object. You just add it onto your, hold on, what am I talking about here? I'm talking about the y component, sorry. So it's even easier than that. So we know VA. So we're thinking now with respect to this frame of reference, the x and y. We're not thinking about these. So VA, and then this one, this 400, it's going down the way compared to the frame of reference. So minus 400 plus, this is going up the way, 200 is equal to 0, because the y components must add up to 0. Therefore, VA is equal to, so minus 400 plus 200 is minus 200. Better be careful with this because the signs are awful important. VA minus 200 is equal to 0. Therefore, VA is equal to 200. So this is drawn on the correct way. We've got a positive result, and it's in kilonewtons. No, it's not. It's in newtons. It's in newtons. So it's drawn on the correct way, and we know that up on the left is positive. The other way people remember this, it's better not to though. The other way people remember this is clockwise positive. It's like the opposite of the moment. But actually for a shear, it's nothing about rotating. You maintain that line. So you maintain that direction of application of the load. So you're better to remember up, left, down, right, positive. So we have got up on the left, so that's positive. Okay, last one now, the sum of the moments is equal to 0. That implies, so what does that mean? Okay, so we're doing it about this point A again. Always you're doing it about this section. Don't have to, but that's what eliminates the most forces. So it eliminates that axial force, eliminates that shear force. So what we would get is for the moments that we have to apply, and it's going in a clockwise direction, so it's negative. So M, should have called that A again, MA. And so we're now, when we're doing these calcs for equilibrium, we're switching back to the positives and negatives for external forces that we've done up till now. And that's in the negative direction. So it's negative MA. And then I'm thinking about rotation around this point. So that 400 has a lever arm of 1 meter, and it's also going negative. It's going in this direction. So that's negative, negative 400 times the lever arm of 1. And then this 200, about this point here, is trying to rotate anti-clockwise, so it's positive, plus 200 times 3 is the lever arm for that, is equal to 0. So let me just have a think about that. It's negative. It's also negative. Okay. Yeah, that's cool. So therefore, just think about if I got that right. I have. Yep. Well, let's just keep working through it, and then if I've made a mistake, we'll go back and find it. Negative MA is equal to 400, negative 400 plus 200. It looks okay. So that's going to be plus 200 equals 0. Therefore, I'll take the MA over and then swap sides. So MA must be equal to, well, better write it out. I'm just thinking it's so important you get the negatives and positives when you're doing this. I'm just going to write it out, even though it takes forever. Minus 200. So we've got negative MA equals minus 200. I've taken that over. So MA is equal to 200. And we're in Newton meters. I tend to write kilonewton meters by mistake sometimes because I'm a civil engineer. I don't work in newtons very often. Okay, and so that's ended up. So even though that, so I've shown it in the right direction to get positive moment, so positive bending moment. So it's clockwise on the left, anti-clockwise on the right, gives sagging. And it's come out positive here, so that's been drawn on in the right direction. Therefore, this is giving us a positive bending moment. This is in the right direction, didn't come out negative. And so therefore, this is bending moment. Is, let's have a think now. Yep, 200 Newton meters. I'm not going to write out the answer again. So let's go back and compare those. So axial force is 0, shear force is positive 200, bending moment is 200 Newton meters. And so what we can see is that it doesn't matter which side you do it on, you get the same answer, including the sign of the answer. So let's go back through what we did here. Oh, and I should just say, and that's how you check your answer. So find it on one side, find it on the other side, and check your answers. You get the same answer on both sides. You know you've got the right answer. Because the internal forces, that's the whole idea, we want to get the same answer on both sides. Otherwise, we wouldn't be able to define exactly what the moment the internal forces were. So what do we do? Geez, a long question. Sorry about that. But we started with the problem. We drew a free body diagram and figured out the reactions. Then we split it at the point we were interested in. We split that beam at the point we were interested in. And then because we'd split it, that reveals these internal forces. So then we take one side and we drew on the shear force, axial force, bending moment. The direction of those we figured out by making sure that we would get, so we've drawn those as if they were a positive internal force. And that, whether it's a positive internal force depends on whether you're on the left-hand side of the object or the right-hand side. So in this one here, we would be on the left-hand side of that object. This one here, we're on the right-hand side of that object. And so the way we draw on these, the direction we draw them on, depends which side we're on, and we make it so that it would give us something positive. Then we switch back to our old way of thinking. We're not thinking about these positive and negatives anymore. We're thinking about just general positive and negative for x and y axes like this. And so in that case, so if this is down the way, we do it negative. If it's up the way, we would, so that's down the way, so it's negative. This is anti-clockwise, so it's positive. This is going right to left, left to right, so it's positive. And we follow that through, just being very careful about positive or negative with reference to the x and y axes, and we'll get an answer. In this case, everything ended up positive, so you didn't really see a situation where you get a negative answer. But if this turned out to be negative, that would mean the shear force at that point would be negative. In other words, we'd have drawn this, we'd have done all our calcs assuming this direction. You get a negative direction at the end, it must be going up the way, which would mean that you had the negative shear force. This would have been negative. So this would have ended up, let me see, like that and like that. And so it would just come out in the wash. You get a negative answer here, so you'd know the shear force was negative. Same thing for the moment. And then you can check your answer using the other side, and you just do all the calcs again, and you make sure you get the same answer. Bob's your uncle. Probably, and then if this was a tube question, I'd also rewrite out the answer clearly. Now that's only done half of it. We've still got to do B, all those forces at B. So let's go through that again with B, and that'll hopefully help make the procedure clearer once we've done it a couple of times. Let me stop there for just now. So now we're doing the same thing for the point B. So we've already found the reactions. So we found internal forces at A. Now we're going to find the internal forces at B. I've kind of dragged this down so that we can refer to that to something a bit neater. So I've already taken the first step. So I've taken that free body diagram. I've split it at B. That's going to make these reveal the internal forces. And so then we're going to work through the various steps. So the first thing we've got to do is to draw on. So we'll use the left-hand side first. I might just move it a little bit more this way, just so I've got more space to put on the forces. So we look at these and we draw on the forces that cutting it has revealed. We draw on those forces, making sure that we're putting them on so that we would get positive axial force, shear force, or bending, or so bending moment or bending. Okay, so positive axial, shear, and bending. So that's how we're deciding which direction to draw them in. And that would mean if we work through and we get a positive answer, it would be positive. If we work through and get a negative answer, then we've drawn it the wrong way around. Should have been the other way around, it would be negative. So it just kind of comes out in the wash if you do it this way. So let's have a look at that. So we need to draw on. Now what I'm going to do this time, we've already learned from the last example that we've got no axial forces on this. There's nothing, if you were to do X and Y components, which I'll just draw on just now so that we can see where they are. So we're always drawing Y perpendicular to the beam. So Y is this way. And we're drawing X in line with the beam. So X would be that way. And then what am I doing? So now we're going to draw on. So we've cut it. To keep it in static equilibrium, we'd need to apply some forces at this end, and those basically are the internal forces. So by cutting it, you're revealing those internal forces. And we're going to draw them on so that they would make positive as per these conventions, this sign convention up here. So for the axial force, positive, we're at the right-hand side, so positive's in this direction. So positive is that way to make tension, a positive axial force. For shear, the convention is if you're on the left-hand side, you should go up. If you're on the right-hand side, you should go down. For this thing here, we're on the right-hand side. So for a positive shear internal force, we should have something going down the way. I'm just going to draw it to the side. It doesn't really matter, you know what I mean. So this is going to be NA, it's a normal force. This is going to be, or your axial force actually, VA, it's just a convention. And then for positive bending, we'd have to have a pure moment going in the anti-clockwise direction on the right-hand side. So we're going to have MA this way. Now I'm shifting my thinking back to the sign conventions that we've been using so far for finding static equilibrium. So I'm kind of shifting back to these X and Y axes, and I'm using the sign conventions to the right, up, and anti-clockwise as positive. So shifting back to that way of thinking. And then we just use our equations. Don't even need to worry. Oh, I said I was going to ignore it and then I didn't. So for this one, we already know that's 0. So let's just ditch that so we don't have to worry about it. What comes next? So you just use your normal equation. So we know sum of Fx equals 0. So we know that axial force is 0. I'm not going to write that out. But the next equation is the sum of the y components must also be equal to 0. In our case, what does that mean? So back to the normal convention, up is positive. So that's going to be positive 200. And then we've got VA. Okay, now B was just to the right of this force. So this force is included. It's like this is a tiny little distance. less than a millimeter or something like that. So it's a tiny distance. We're not even going to worry about it. But the force is on this side. And so therefore, that force we have to allow for, it's going down the way, so minus 400. And then we've also got VA, it's going down the way, so it's also minus 400 is equal to, oh, sorry, don't know why I wrote minus 400. It's minus VA. So it's also going down the way. And there's no other vertical forces, so that equals 0. So no other y components. So therefore, 200 minus 400, that is going to be, I'm just thinking ahead here to see if I'm going to get the right answer. I haven't made a mistake. So we've got it minus 200 minus VA is equal to 0. I know this shear should be negative. Therefore, VA is equal to 200 kilonewtons. So it's positive. I'm pretty sure it isn't. So we're up 200. You come along here, you go down 400. It's minus 200. And then VA should be down on the left. That's correct. Yeah, I made a mistake. So that's, why did that go negative? So I took this over to the other side. So that's 200. And so therefore, this is negative V equals 200. So therefore, VA is equal to negative 200 kilonewtons. So in fact, the way we'd drawn this on was the wrong way round, if you know what I mean. But we do draw on this way, because that would give us a positive shear. So that's actually the other way. That force should be going up the way. If it's going up the way, we've got a negative shear. And so it all comes out. So the shear at shear at B is equal to minus 200 kilonewtons. And there's a trick. The reason I knew I was wrong is because there's a quick way to do this that I'll show you later when we get to shear force diagrams and bending moment diagrams. And so I knew it had to be minus 200 kilonewtons, and then I found out where I'd made a mistake. So I'd taken this over the other side, but it also made this positive, but it wasn't. So this is negative, comes over positive 200, but this is still negative. Therefore, VA times both sides by negative 1, VA is minus 200 kilonewtons. So the shear at B is minus 200 kilonewtons. It's one of our answers. I'll underline it rather than write out the whole answer again. Okay, the next thing is the sum of the moments should be equal to 0. What does that mean? I'll do it here. I think I should have enough space. So we're going to take the moments about B, gets rid of a heap of forces. This is just to the right, so we're actually going to assume this is right on B, if you know what I mean, but we're drawing it on this side. So it's just to the right of that, but it's going to essentially be 0 moment. It's going to have such a small lever arm, it's going to be neither here nor there. It's the idea. So let's work out what all our moments are. We've got 200 newtons going up the way, we've got a lever arm of 2 meters, and it would be going clockwise. So that's negative 200 times 2 meters. Then what else have we got that's causing a moment? Nothing. This has pretty much got 0 lever arm. This one's 0 lever arm to be, but we've got that moment. Okay, so the moment is always, you could put that anywhere, and so you just add it onto your moments. So, and it's going anti-clockwise, so it's positive. Plus MA equals 0. Therefore, MA, so it was already positive, take this one across, it's going to become positive, is 400. Did I do kilonewtons? Apologies. Just looking back. So it's in newtons, told you, civil engineers not used to using newtons. 400 Newton meters. Fair enough. Now, if we've, so what it means is, so this time this is the right way around, therefore it is a positive bending moment, because it's this one here. So it's positive, so that's correct. So it's still a positive net bending moment, but it's a negative shear. How did we know that? Well, we drew it on as if the shear would be positive, so we drew it on down the way on the right. That would be a positive shear. But when we came through, it was negative, that value for VA. Therefore, we know it's the wrong way around. It would actually be up the way, and so therefore it must be a negative shear. So we know the shear is negative. And so the moment at B is equal to 400 Newton meters. Okay, so I'll quickly run through the check. To do the check, I'll use the other side. I'll try and squeeze it in here if I can, so I don't have to go off the page. And hopefully we'll get the same answers, both in terms of the magnitude and in terms of the sign. Okay, so on the other side, you should get the same answer, shouldn't matter which side you use, as long as you're careful about your drawing on these so that these are positive. Then you work through the calcs using the normal convention, and then this result here, whether it's positive or negative, will tell you whether the shear itself is positive or negative, or the moment, the bending moment. I should be careful about this. It really should be bending moment here, not moment. So usually when you're, it's a bit of a, being a bit pedantic, but when you're talking about a pure couple, you might call that a moment, whereas when you're talking about the internal force, you tend to talk about the bending moment. It's an internal force, it's a bending moment. Coolio. Okay, I'll do the quick check, and then that's us done for this example.